All right, everyone, get ready because
Wow.
today we're diving deep, and I mean deep, into the world of nuclear fusion. And don't worry, you don't need a PhD in physics to follow along. You sent over some seriously cool stuff on this topic, so we're going to break it all down. What actually is nuclear fusion? How does it work? And most importantly, why is it considered such a potential game changer for the future of energy? So, to kick things off, we're going to take a quick trip back in time, explore the mind blowing physics that makes fusion possible, and then we'll get into the really exciting part the hurdles scientists are tackling right now to try and make fusion power a reality. Ready? All right, so picture this. It's the early 1900s. Einstein has just blown everyone's minds with Imsihar, and suddenly energy is this whole new ballgame. And it's right around this time that scientists start realizing something incredible about the stars, those giant balls of light in the sky. They're not just shining, they're absolute powerhouses, fueled by a process so energetic it makes even the most explosive chemical reactions look like, well, a damn squib. And that process, my friends, is nuclear fusion. Enter William Draper Harkins, an American chemist who, way back in 1915, proposed something truly radical. What if, and this was a big what if at the time, what if atomic nuclei, those tiny hearts of atoms, could actually combine and release energy in the process?
It's actually mind-blowing when you think about it right.
Yeah.
Harkins was basically peering into the future of physics, because back then the atom was still this mysterious entity. To even suggest that these tiny things could merge was a huge AKE deal.
Well, talk about a light bulb moment, right?
Mm.
But then along comes Arthur Eddington in 1921, and he takes this wild idea even further. He connects the dots between Harkin's fusion idea and the sun's insane energy output, suggesting that the sun itself might be powered by this process.
And what makes Eddington's insight even more impressive is that at that time, they didn't even fully understand the structure of the atom. The fact that he was able to deduce that only nuclear reactions, specifically the fusion of hydrogen into helium, could explain the sun's energy output. It was a stroke of genius.
Okay, so we've got stars fusing away up in space, doing their thing, but what about us here on Earth? Could we, recreate that kind of power down here? Well, in 1932, Mark Oliphant steps up to the plate and actually achieves lab created fusion for the first time. Now, this wasn't the controlled, energy producing kind of fusion we're aiming for today, but still, it was proof that fusion wasn't just a cosmic phenomenon. But then things take a bit of a turn toward the, shall we say, explosive. Fast forward to 1952, and the world witnesses the awesome, terrifying power of the first hydrogen bomb test Ivy Mike. Uncontrolled fusion, check. Harnessing that power for steady, clean energy. Well, that's the multi-billion-dollar question that still has scientists fired up even today. Okay, so we know fusion is powerful. We know it has insane potential, but we've also hinted that it's not exactly a walk in the park. So how about we break down the science of fusion just a bit, get a feel for what's actually happening at the atomic level?
Absolutely.
Hmm.
At its heart, fusion is all about forces, specifically overcoming them. Imagine trying to push two really strong magnets together with the same poles facing each other. They resist, right? They really don't want to touch. That's essentially the Coulomb force, the repulsion between, like, charges at play on an atomic scale. And in fusion, we're talking about forcing positively charged atomic nuclei to get so close that they fuse together. And trust me, that takes an incredible amount of energy to overcome.
Okay, so just like those magnets, it's all about overcoming that natural resistance, that pushing and shoving at the tiniest level imaginable.
Exactly. And here's where it gets even more interesting. The lighter the nuclei, the easier they are to fuse.
So, like, smaller magnets are easier to force together than those giant ones that could pull a car apart.
Perfect analogy. And that's why hydrogen, the lightest element in the universe, is the star of the fusion show.
So that's why everyone's so focused on hydrogen. It's the easiest to work with, fusion-wise.
You got it. And not just any hydrogen, but two special flavors of it, deuterium and tritium. They're isotopes of hydrogen, meaning they have extra neutrons. And when these guys fuse, they create helium, which is completely harmless, by the way, a neutron, and a truly mind-boggling amount of energy. We're talking millions of times more energy, pound for pound, than you get from burning fossil fuels.
Now, that is what I call bang for your buck, energy-wise. No wonder fusion is considered the holy grail of energy production. It's like we're talking about a future where energy scarcity is a distant memory. But, as we've kind of hinted at, if it were easy, we'd all have fusion reactors powering our homes by now, wouldn't we? So let's get into the thick of it. What makes this whole fusion thing such a massive scientific and engineering mountain to climb? What are the real roadblocks we're facing?
You're not wrong there. It is anything but easy. I mean, think about it. To get fusion to happen, We need to create conditions
Yeah.
kind of like the core of the sun.
Okay. Yeah, that's a bit beyond my usual cooking temperature, so it's not as simple as just, lighting a barbecue.
Uh-huh. No, not quite. I'm
Yeah.
talking about temperatures 10 times hotter than even the surface of the sun. Millions of degrees.
Yeah, my oven's got nothing on that. But okay, let's say we could somehow get things that hot. How on earth do you even hold on to something like that?
The multi-billion-dollar question. Remember that plasma we talked about? That swirling soup of charged particles? We need to contain that somehow, but it can't touch any sort of physical container.
Because it would just vaporize it instantly.
Exactly. Gone in a nanosecond. It's like trying to hold lightning in a bottle, but 1,000 times more extreme.
I'm getting a sense of the challenge here. So how are scientists even starting to approach this? What's the game plan?
So the big challenge with fusion boils down to one word: confinement. We have to figure out how to hold this crazy hot, energetic plasma captive long enough for those fusion reactions to happen and release enough energy to actually be useful.
So it's not just about heat, it's about containing something more extreme than we can even really wrap our heads around.
Right, and there are two main strategies being explored right now, both super ingenious, both incredibly complex.
Okay, lay it on me.
So the first one is magnetic confinement, and the second is inertial confinement.
Okay, those sound pretty different.
They are, but they both aim to achieve the same thing: controlled fusion.
Let's start with magnetic confinement. How does that even work? I mean, how do you contain something with magnetism?
Well, got to go back to high school physics for this one. Remember how electricity and magnetism are like two sides of the same coin?
Yeah, vaguely.
Basically, charged particles, like those in our plasma, they're influenced by magnetic fields. So if you can create a strong enough magnetic field, you can use it to trap the plasma, suspend it in a vacuum chamber so it doesn't touch the walls.
So it's like an invisible force field holding the plasma in place? That sounds like something out of Star Trek.
Haha. It does, doesn't it? But this is real deal science, and it involves some seriously sophisticated engineering. And within magnetic confinement, there are different reactor designs. The most promising ones right now are called tokamaks and stellarators.
Tokamaks and stellarators, that
Yeah.
do sound kind of sci-fi. What's the difference?
Picture a donut.
Okay, donut. Got it.
That's basically the shape of the magnetic field in a tokamak. And it's incredibly powerful, helps contain that plasma. Stellarators, on the other hand, they take that donut shape
Yeah.
and they kind of twist it, make it even more complex to try to improve that confinement even more.
So we're talking about creating these miniature suns, holding them in these incredible magnetic fields. What does that even look like? Like, how big are we talking here?
And this is where it gets even more mind-blowing. One of the most ambitious projects right now is called ITER, the International Thermonuclear Experimental Reactor.
ITER, yeah, I think I've heard of that. It's massive, right? Like a global effort to make fusion power happen.
It is. It's a collaboration between 35 countries, all pooling their resources, their expertise, to build the world's largest tokamak. We're talking gigantic.
Yeah.
Magnets taller than a house, weighing more than a jumbo jet.
Wow, that just puts it into perspective.
It's one of the most complex engineering projects ever attempted. But if it works, if they can actually achieve what they're aiming for, ITER will be a game changer. It'll demonstrate that sustained, stable fusion power is actually possible.
I can only imagine the celebrations if they pull that off. But okay, we've been talking a lot about magnetic confinement. What about the other one, inertial confinement? How's that different?
So inertial confinement takes a slightly different approach. Instead of using magnetic fields to confine the plasma for a long time, it aims to achieve fusion extremely quickly.
Okay, so it's like a quick burst of fusion energy instead of a continuous flow.
Exactly. Imagine you have a tiny pellet of fusion fuel, smaller than a grain of pepper,
Okay, got it. Tiny pellet.
and you hit this pellet with incredibly powerful lasers or particle beams from all directions simultaneously.
All at once.
Wow. Yeah. This creates immense pressure, immense heat, causing the pellet to implode, basically.
So instead of a slow and steady burn, it's like we're trying to create a miniature supernova.
You got it. And in those few fleeting moments, the nuclei within that pellet fuse releasing that burst of energy.
That sounds incredibly precise, like you need insane levels of control to pull that off.
Oh, absolutely. And it brings us back to our earlier discussion about the fuel, deuterium, and tritium, remember?
Yeah, the special types of hydrogen.
Right. Well, the choice of fuel and the type of reaction we want, they play a huge role in how we design these reactors, whether they're magnetic like ITER or inertial confinement.
Right, so different tools for different reactions. It's all starting to come together now. We talked about the different types of fusion reactions before, but is there a connection between the type of reaction and which confinement system you'd use?
Absolutely, there can be. And to understand why, we need to talk about a very important concept in fusion: neutronicity.
Neutronicity. Okay, that rings a bell, but could you give me a quick refresher on what that is exactly?
No problem. Neutronicity basically refers to how many neutrons are released in a particular fusion reaction. So remember how we said deuterium and tritium fuse? They create helium and a neutron.
Yeah, that's the energy release, right?
Exactly.
Huh.
And that neutron carries a lot of that energy. But here's the thing. Too many neutrons can actually be a problem.
Oh, so it's like a double-edged sword.
Exactly. While neutrons are great for carrying energy, they can also damage the reactor materials themselves. Over time, this bombardment can make the reactor materials radioactive, which creates all sorts of challenges in terms of engineering and safety concerns.
So it's about finding that balance, right? Enough neutrons for energy, but not so many that you create a radioactive mess.
You got it. And that's a really important consideration when scientists are choosing which fusion reaction to go for a particular application.
Makes sense. It's all about picking the right tool for the job, even when we're talking about recreating the power of a star.
And speaking of picking the right tool, some scientists are really excited about what are called aneutron fusion reactions.
And you try, oh, right, those are the ones that produce very few neutrons, or even none at all, right?
You got it. And the idea of an aneutron reactor is very appealing for a whole bunch of reasons.
Yeah, it sounds almost too good to be true. No radioactive byproducts, easier containment. What's the catch?
Well, the catch is that they're much, much harder to achieve. They require even more extreme conditions than the deuterium-tritium reaction we've been talking about.
So it's like aiming for the next level of fusion, potentially even cleaner and safer, but with an even steeper climb to get there.
That's a good way to put it. And that's the story of fusion research, really. Every answer seems to lead to even more fascinating questions, and every challenge we overcome opens up new possibilities we hadn't even imagined before.
It's amazing to think about. We're really on the frontier of something incredible here. But we've talked a lot about the how of fusion, the mind-blowing engineering, the different reactions. But I think it's time we shifted gears and talked about the why.
I agree. We've gone deep into the science, but now it's time to explore the reasons behind this incredible quest for fusion power. What's at stake, and why should we all care? That's what we'll unpack next.
Yeah, you're right. The why is crucial. I mean, we've covered the mind-blowing science, the incredible engineering challenges, the different types of reactions, but why are we so fixated on making fusion power a reality? What's the ultimate payoff?
Imagine a world where clean, safe, and practically limitless energy is just the norm. Not a dream, but how we power our civilization. That's the promise of fusion.
Okay, I'll admit, it does sound pretty utopian. No more fossil fuels, no more scrambling for resources. Is that what we're talking about here?
It's a bold vision, definitely.
Okay.
And look, no single technology is a magic bullet, right? But fusion has the potential to completely revolutionize how we power our world. And I'm not just talking about keeping the lights on.
Okay, so it's bigger than just energy.
Exactly. It's about sustainability, climate change, global equity, things that impact all of us.
So how does fusion actually change things? Break it down for me.
Well, for one, fusion could provide what we call base load energy. It's constant, it's reliable, it doesn't depend on the weather like solar or wind.
So it's like a rock-solid foundation for all our energy needs, no matter what.
You got it. And unlike those renewables, we can generate fusion power 24/7 anywhere in the world, regardless of sunshine or wind patterns.
Okay, that's huge. But what about the nuclear power we already have? Fission. How does fusion compare to that?
Ah, that's the key difference. Fission relies on splitting atoms, heavy elements like uranium, and it creates radioactive waste. Fusion, on the other hand, uses abundant hydrogen isotopes, and its byproducts are minimal, mostly just helium.
Helium, like the stuff in balloons.
Exactly. Harmless, even kind of fun. Talk about a stark contrast in terms of waste products.
Okay, I'm convinced safe, clean, abundant. It does sound like the Holy Grail. But with all this potential, why haven't we cracked it yet? What's holding us back?
To be blunt, fusion is one of the most challenging things humanity has ever tackled. We're talking about recreating the conditions at the heart of a star here on Earth.
Yeah.
The temperatures, the pressures, the sheer forces at play. It's incredibly complex.
It's almost like trying to, I don't know, hold a star in a jar. So how do we even begin to approach something so ambitious?
It takes a mix of scientific ingenuity, collaboration on a global scale, and, yeah, A good dose of human stubbornness. It's not just about building bigger machines, so that's definitely part of it. It's about pushing the boundaries of what we understand about the universe itself.
So it's not just about solving our energy problems, it's about pushing the limits of human knowledge and pushing ourselves to do things we never thought possible.
Exactly. Every experiment, every simulation, every new material we discover, it brings us closer to unlocking fusion's potential.
And speaking of potential, we've focused a lot on energy, but you mentioned earlier that fusion could have even wider applications. Like what?
Oh, the possibilities are huge. Take medicine, for example. Fusion could revolutionize medical isotope production.
Medical isotopes, those are used in imaging and some cancer treatments, right?
Yeah, exactly. Right now, we produce them with aging fission reactors, which is expensive and not very efficient. But fusion, it could be a game changer for producing these life-saving isotopes.
Wow, so we're talking about potential impacts on healthcare, on people's lives, even beyond just clean energy.
Absolutely. And that's just the start.
Hmm.
What about space exploration? Imagine spacecraft powered by fusion engines capable of reaching other planets in a fraction of the time it takes now.
Okay, now that's getting into Star Trek territory. Interstellar travel powered by fusion. Is that even remotely possible?
It might sound like sci-fi, but the principles are sound. Fusion propulsion could drastically reduce travel times, opening up the solar system and maybe even beyond. We could be talking about reaching other stars within a human lifetime.
That is mind-blowing. We started by talking about the power of stars, and now we're talking about using that same power to explore the universe. It really highlights how profound this technology could be.
Exactly. Fusion research isn't just about solving our energy challenges, though that's a huge driving force. It's about expanding our understanding of the universe, pushing the limits of human ingenuity, and shaping the future in ways we can only begin to imagine.
Well, I think it's safe to say that after this deep dive, I'm utterly convinced. Fusion is more than just a scientific endeavor. It's a testament to human ambition, our curiosity, our drive to reach for the stars, literally. Thank you so much for joining me on this incredible journey into the world of nuclear fusion.
The pleasure was all mine. It's been a fascinating conversation.
And to our listeners, we hope this has sparked your curiosity about the incredible potential of fusion. Until next time, keep those minds hungry for knowledge, and we'll see you on our next deep dive into the wonders of science and technology.